Okay. Fibonacci. So, are we all familiar with the Fibonacci numbers from the C course, right? CNG 140? Okay. I'm going to write down the Fibonacci numbers. In computer engineering, it starts with 1, right? 1 and 1. And then the next Fibonacci number is the sum of the previous two numbers. So we are going to have 2. These two sum 3. These two sum 5. Goes so on, right? So we are going to implement this function with MIPS. And what are we supposed to do is not an iterative function, but a recursive one. So if you remember, the recursive functions are the ones that calls themselves repeatedly. So the trick about the recursive functions is given the number of inputs, we don't know how many branches, how many jumps that recursive functions would ever make. So I'm going to map this on my mind to how to call the function itself. It's actually written in C here. I'm going to write it down for convenience. So we have a function int Fibonacci. It takes a function, right? If n is equal to 0, then return 0. Else if n equal to 1 is return 1. Else, which means n is neither 0 nor 1, right? We have return Fibonacci n minus 1 plus Fibonacci n minus 2. Okay. All right. How I would implement this function? Let's take a number. Okay. Let's take a Fibonacci number and let's break it down. Like, let's take 5, right? 5 is like what? This is n is equal to 0. This is 1, 2, 3, 4. Right? So this is Fibonacci number 4. So we have F4, right? And it is the sum of F3 and F2, as n is not equal to 1 or 0. So this F3 should call itself again, right? This is F2, F1. F1, we have a return value for 1, right? So for F2, it is F1 and F0. The same goes with this one. We have a repetition of this branch, but it's separate. So it's, again, another F1 and F0, right? Are we missing anything here? No? Okay. I think this is for N3, right? We have this F1, and this F1 right here. Okay? All right. So as we don't know how many branches we will make, and we sure will need, as we go down this tree, all the way down to the leaves, that as we are done, as we return some values, we will need to return to the upper one with few things. Those would be the return address, right? We have a return address that we should return to the previous point that we were at. The sum of its branches, right? The sum. And number n, right? So that we would know the n2 in this case is the sum of its branches. So we need the number n. Okay, I'm going to assign n to the register A0. and I'm going to assign this to S0. So each time, as I don't know the number of repetitions, I need to retrieve these data from my code, right? So what should I use? Any suggestions? Anything? No? Okay, I'm sure you have seen the stack in the literature, right? In your course. So a stack is, you know what a stack is? It's actually a map of registers. It's usually placed in the memory, okay? And we have a pointer, stack pointer, that points the next available room in the stack. And you know how a stack works? It's last in, first out. So it's like a stack of plates that we put plates on top of each other, right? And then the first place we take back is the last place we actually put there, right? You could also use queues, but that wouldn't really serve to the purpose in our case, right? Because we are going to put, as we go down here, let's say we are at F2 and we sum these up, we have to return to the last item, last data that we stacked, and which is F2. That's why instead of queues, we use stacks for this one, okay? All right, so how Fibonacci numbers work? How this code should work? We would probably have many stack pointers, many jumps, many branches, but usually for these such complex examples or questions, I would recommend you to break down your codes and write them separately and then fit it all together to have a one segment, okay? So I'd like to start with the return values. We have some if statements, right? We have the if statements to implement. If, else if, and else. We have some return functions, 0 or 1, depending on the value of n, if it's equal to 0 or 1. And we have a return function that calls itself, right? Fibonacci n minus 1 plus Fibonacci n minus 2. So we have recursion, I see here, and I see a sum function, right? Okay, so I need to implement these, each of them at once, and one by one, and then I'm going to put it all together to implement the Fibonacci, okay? All right, let's start with the easy one, maybe, the sum. So, how are we going to implement the sum function? We sure will need an add, right? So we are going to add two numbers to a register. So this is the destination RD, this is RS, this is RT. So these should fill with the values from the Fibonacci retrievals, okay? So when I sum these numbers, where should I get them from? So each time I'm referring to the stack now, recursion right here. Each time I will call the function itself, right? So, and before calling the function, I need to store my data to the stack, right? So I'm going to have, I need to initialize the stack pointer, right? I need to make some room, and you know how a stack pointer works. So it is stack pointer to itself with which number? So I have 3 data, each of which has 4 bytes, and I have 12 bytes in total. So I have to make room with adding this stack pointer address, some offset, so that I would shift it and make some room and then push my data. It is 12. What do you think? It should be minus 12, right? Because I'm making room downwards, so you can, yes.
How we determine minus 12? How we determine the minus 12?
We have 3 data, return address, the sum, and the n. So we have 3 registers, right? Sum, the result, the n value, and the return address, that not to get lost, okay? And each of which has 4 bytes, which makes 12 bytes in total. And that's how we initialize the stack pointer. And then we have to store these data, right? Start with return address. Okay. So with which offset that we should store this return address first? So I have the stack pointer where? Here or here? Should be here, right? And we make room for 3. And I want to put my return address here. So I need to have an offset of 0, 1, 2, 3, 4, 5, 6, 7, 8. The 8th byte after the stack pointer, so that I would push to the very bottom of my stack, right? So it should be 8. Okay, clear? Next, I need to store. I said my sum would be in S0, right? So likewise, it is S0 stack pointer, and this time it should be 4. And next, store instruction will be for A0, and with an offset of 0 to itself, to the top layer, okay? All right, so each time, this statement is important, the structure. Each time I would call a function after saving my in previous state, I should check with the if statements, right? So I'm going to check if n is 0, I'm going to return 0, and if n is 1, I'm going to return 1, and otherwise I'm going to come back to here. So which value should I check for first? Should it be 0 or should it be 1? Actually, it doesn't matter, but which one proves to be more efficient? What do you think? Because the question asks for the least line of code. 1? If we check with 0, let's think about it. If we check with 0 first, if n is 0, we branch to somewhere else, but we don't know if n is 1 still, right? So we should check again if n is 1, right? So 1 is larger than 0. So if it's 0, that we have, we might still have a chance that n might be 1 after all, right? If we would check with 1 first, say if n is larger than 1, so there are 2 options, right? Actually, we are using the equal to instruction. If we are using 1 is equal to our variable, then we would branch. But now this leaves 2 possibilities. Either n is larger than 1 or n is 0. If we use other way around, if n is larger than 0, it's larger than 0. Okay? So both types work, but I would use with checking with the 0 first. Okay? All right. So after this, I'm going to use BGT, which stands for branch if greater than. I'm going to come to test 2. So I'm checking my A0, which is my n. If it's greater than 0, right? If it's greater than 0, it's either 1 or even larger. So if it's greater than 0, I go to test 2. Why? I know that my now I know my n is larger than 0, but I still don't know if my n is larger than 1. So I have another test 2, right? To check if my n is 1. So to check with 1, I don't have a 1 register, right? I have 0 register. So I need to create some temporary register. I store 1 into it, and then I'll check with A0. So I'm going to have a simple immediate instruction, which is I'm going to use T0 for it. Register 0, 1. So I have T0 as 1 here. And then I'm going to branch if not equal T0 A0 to some other place now. So if my T0 or A0 is not equal to 1, now I'm going to go to the place where I should sum the numbers, and before summing them, call this function again, right? Yes. Come again? Mm-hmm. To here, you mean? It should branch back to here or to here? Yes. This. Okay. We should check with 2 conditions separately, right? So what you would suggest is to first check with 1, and then if it's not equal to 1, that I told at the beginning that it's either larger than 1 or it's 0. So this branch if greater than instruction makes sure that it is greater than 0. Otherwise, if we check with 1, we would not be able to use branch greater than. We would use, as you said, branch not equal or branch equal, right? If we would use branch equal to 1, then we wouldn't know if this is 0 or 1. So we wouldn't be able to use branch greater than. Instead, we could use branch not equal or branch equal to, but this leaves the same line of code. So it is, if we would use, okay, like if we would use branch not equal, maybe, if A0, this is, let's say, T0, right? And we take this add immediate to here, right? I'm just going to put a temporary arrow. So this code is here, and we check with if it's equal to 1, we go to test 2, and test 2 checks if this is actually, this S0 is equal to 0 or not, right? The only thing we would do is to change the order. That's still fine. The thing with the solution is actually it uses T0 after this to somewhere else to shorten the code, but that's still fine. We can generate it again. So it's up to now, it's perfectly fine. It's the same. Okay. So we checked if this is equal to 0 first here, right? If it's not, then we need to have something here. If it is equal to 0, we need to assign the return value as 0. So we first need to create it, right? So are you familiar with the V registers? V0, V1, V2. Those are simply registers actually, like A, V, S. They don't really matter. But the initials are to indicate, to encourage you not to confuse in such functions. So V is used usually for such recursive functions, for returning values. So we just stick with the tradition, okay? So I'm going to use the V register to return my zeros and ones and other values, okay? So it is add V0, 0, 0. So this is the place I checked if my branch instruction is equal to 0. I'm just going to put it back. That's a good point, by the way. Okay, 0, T0. Okay. And what should I do after this? So I actually found something. For among those return functions out of the 3, I found out that my first one actually works, fits the condition, right? And I'm actually returning back to an upper state in my tree. And what should I do for returning? I need to find the return address, and I know somehow, thanks to using the stack, that the last item I stored is actually belongs to one upper state of the same function. So the last item I stacked in my stack, let's say I came all the way here and I found 0, right? So for coming here, I stored this first, and this is not equal, doesn't satisfy the conditions. I come back here, down here, and then I branch to 1 and 0. And I first checked with 0. It fits. I should return to F2, right? And due to the nature of the recursion, it will check with F1, and it will return the value again, which I will implement very soon with the add function I wrote over there. And then it will sum these up. It should return with the upper function. Is this clear? I know it's a lot of tricky, so it's important for you to able to see this. It's the nature of stack. The objective of the question is for you to implement recursion, besides to be able to utilize the stack for such questions or problems. Okay. So I found a condition. It is 0. So I would jump to some return segment. I'm going to put J return here, and I'm going to write return, and to use this space. So return segment. As I told you that you don't need to write everything in a one line, so just make them separately first and then combine them all together. Okay. So I really don't know that where should I put my return. Maybe here, but maybe something else would come up there first, right? Before the return address that I would need urgently. So I'm just putting return somewhere else, and then I'll put it to where it belongs later. And as long as it's branching, it's for now it's fine where I branch to, because it doesn't matter yet. The return address should be, return code should be, I should retrieve my data from the stack, right? So where do I start with? Remember the stack of plates? The last in, first out. So I should retrieve the last one that I put and move on. So the last one that I put in the stack was the A0, right? It's at the top layer of the stack. So I'm going to load word A0 with this offset in the stack pointer. And then I load the next one is S0, the sum, right? For offset with stack pointer, and load word RA8 stack pointer. Am I done with the stack? I want to leave the stack that's in the state that I actually found it in the first place. So that means that I first initialize my stack pointer and then store the values. I retrieve them back. So I need to put the stack pointer back to where it belonged in the first place. So I need to give offset back to the stack, which is add immediate stack pointer to itself with 12. Number 12 refers to 12 bytes. Okay. Alright. This is how I would return. Okay, now let's continue. We were here. We returned to jump. So this actually doesn't matter where I put it, where I initialize it, because the code before is instruction before is jump. So from here I will never come here. So it's okay if I put this here. So if I move on with this branch condition, say if it's not equal to 1, go to some other segment. But if I go move on, that means that my n is equal to 1, right? So I'm going to create a 1, and this leads to your question that why didn't we use this at immediately here and check this 1? What the solution does, we don't necessarily need to do this, but this is pretty efficient way to do it. We already generated some 1 here to compare. So what it does, it equates this register. It already utilized 1, so it's using this utilization to create the result in our result register, sum register. Okay. Okay, and that is I was using my B0, right? With 0 and C0. You could use immediate instruction also. That's still fine. This still doesn't make any difference in terms of how many lines that you're using. And then we go to return. Right? I'm done with this, so I need to go to this return and store my variables back as I'm done with it. Okay. So what if the n wasn't equal to 1 or wasn't equal to 0? And in both cases, I checked with this condition, and this condition also didn't match. So I jumped to some other set. So this is the tricky part where we call the recursion function to sum the values. Okay. So n is not equal to 0 or equal to 1. First thing I do is I first go to n minus 1, right? If it's f4, I go to f3. So it is add immediate, this is generate. A0 itself with minus 1. So what I get here is n minus 1, right? I can play with the n as long as I have the initial value, the original value in my stack. Okay, and then I have n minus 1. I need to go to the function again, right? And the function starts with the stack pointer, storing the value. So jump Fibonacci. It's and I put Fibonacci. You can play with the names. So I should go this routine again, right? What would be a mistake here if I jump? So I already store my return address, right? But I don't store the return address of this code, right? So when I jump, do with the Fibonacci and all, I need to return here and then continue, because I still have the n minus 2 to process it. So jump wouldn't be an appropriate code here. Instead, we say gel, it is jump and link. So it jumps to some segment, as in C its function. When it's done, it directly comes back to the return address of this place and then continues, right? And if I ever return a value, which I will return eventually, it's stored in V0, right? We talked about this, and we will add this V0, whatever return, to the sum, which is S0, right? So I'm going to have the add function to S0 from V0 is to 0. So I copy the code, add up whatever I returned to the S0 here. Now I need to go to n minus 2, which is an immediate A0 minus 1. So this is n minus 2 now. And then I need to go to the Fibonacci code again. And then I need to add S0, S0, right? V0. So I need to add up to the S function, which means that I should better use S0 and V0 here as well. Did you guys catch this? So I'm adding up to S0 with the value of whatever V0 has returned.
V0'ya return yapmamız gerekmiyor.
Yes, we already returned, we already assign a value to V0 in that segment, code segment there, and then we put the V0, it's stored there. It's either 0 or 1. So we add either 0 or 1 to S0 and store it back to itself. Okay? So what is this now? This is Fibonacci n minus 2 plus n minus 1. Is this clear for you guys? So I actually implemented all the functions. The only thing left is to put this all together. Right? I have the first code here, the second here, and the third here, right? So let's see here. If it's not equal to 0, equal to 1, it goes to gen, and if it's 1, it goes to t. It adds the value to t0, right? So maybe I can add some jump here, and then where should it jump to? Immediately. Maybe return, not return, because I have, and if it passes here, right, that means it's actually 1, and it should return some value, and that return value is actually where this code, right? So we have a 1 there, and then oh, first we need to store back the stack, right? So we have to have j return here. As long as I have j here, there, I can just put this code below that one, because it will never reach there. And after this, I can simply put my return. So when I sum this is also tricky. When I sum these two numbers, the next thing should I do is to go up in the stack again, right? I'm talking about the intermediate leaves here. I'm talking about like F3 and F2. Step. I have the sum of this. I need to return to the upper state, right? So I should maybe jump return again here, or you can put the return code just below this, so that we will say the line, right? So this goes first, and then this segment goes second, and that segment goes last. Is this clear? If so, we can have a break, if you guys like. Okay.